Keeper 8.7, exponential growth and decay. Our law of natural growth and decay is given by dy over dt equals ky. And the theorem that we need to know for this, using that law that we just looked at, is y of t equals y of 0 e to the kt, which you kind of saw back in the day when you guys did like APERT with compounded interest, when you learned that in like Algebra 1. All right, so the first example says use the fact that the world population was 2560 million in 1950 and 3040 million in 1960 to model the population of the world in the second half of the 20th century. Assume that the growth rate is proportional to the population size. What is the relative growth rate? And use the model to estimate the world population in 1993 and to predict the population in the year 2020. All right, so the first thing I'm going to do is I'm going to set up like a little equation for the information I know. So I know that I know that the population in 1960 was 3040, and so that's like my final population up to what I know. All right, so I'm going to set 3040 equal to my initial population, which was 2560, e to the, well, there was 10 years that passed between 1950 and 1960, so I have 10k. Now I can use this information to figure out what k is, or my rate of proportionality. So I would divide both sides by 2560, and then I would ln both sides and divide by 10. That gives me my k of 0.0172. In other words, I have a growth rate of 1.72% per year. All right, so the next thing says use the model to estimate the population in 1993. Well, if our initial number starts at 1950 to 1993 is 43 years, so my t is 43. And so I'm plugging that into my formula, and I have P equals 2560 e to the 0.0172, that's what we found in the last step, times 43. I'll plug that whole thing into my calculator, and I'll round accordingly because we are talking about people. So I get P equals 5,363. And then the second question, or the third question, says what's the population in 2020? So that would be T equals 70, and I'd plug it back into the same formula, and I get a P of 8534. All right, so the next question says the half-life of radium-226 is 1590 years. A sample of radium-226 has a mass of 100 milligrams. Find the formula for the mass of the sample that remains after T years. All right, so again, I'm just kind of messing with that formula that we started with, and since they told us that it had a half-life of 1,590 years, I can set up a formula that I can just say, well, the half is equal to e to the 1590k. And I can use that and I can solve for k. So I'd ln both sides, and I wrote it as negative ln2, but it's the same thing as ln of 1/2 using log rules. So negative ln of 2 equals 1590k, and then I divide by 1590 and I get k equals negative ln2 over 1590. All right, and so if I use that k, I can plug it into my formula, so I get y equals my initial amount, which is 100, e to my k, which was negative ln2 over 1590, times t. Next question says find the mass after 1,000 years, correct to the nearest milligram. All right, so all I'm going to do is take my formula, plug in 1,000, throw that in my calculator, and I get 65 milligrams. Last question says when will the mass be reduced to 30 milligrams? So I'm going to set my equation equal to 30. I can either use my calculator and do the solve feature, or I can divide by 100 and ln both sides. But either way, if you work that out, you get t equals 2,762 years. All right, next example says at any time t, the rate of increase in the area of bacteria is twice the area of the bacteria. If the initial area of the bacteria is 10, then what is the area at time t? So again, I'm going to start with this idea that they started me with that said the rate of increase of the area of bacteria is twice, so 2 times the bacteria. So I'm saying dA over dt is 2 times A. All right, so basically what I'm doing here is I'm solving this differential equation. So I'm getting all my t stuff on one side and my a stuff on the other side. So I multiply by dt and divide by a. All right, once I do that, I integrate both sides. I end up with ln of A equals 2t plus c. Notice that I didn't put absolute value on the A since we're talking about like the bacteria. Like we're not gonna have like a negative amount. All right, so next I'm gonna e both sides, so I get A equals c e to the 2t. And then I know, again, they told me the initial amount for this bacteria, or the initial area of the bacteria is 10. So I know that my C, in this case, look how your formula is set up almost like your A part. So your C is 10. So we have area equals 10 e to the 2t. All right, the next example says the number of bacteria in a culture is growing at a rate of 3,000 e to the 2t or over 5 per unit of time t. At t equals 0, the number of bacteria present was 7,500. Find the number present at t equals 5. Well, I'll start with the idea that we have this growth rate. So we have dB dt equals 3,000 e to the 2t over 5. And so I'll solve this out like a differential equation. I'll multiply both sides by dt. And then I'll integrate both sides to get b equals 7,500 e to the 2t over 5. Now all I have to do is plug in the t that they're asking for, which is t equals 5. And when I plug that in, I get b equals 7,500 e squared.